Welcome to EDUCARE. Today in this video, the rotating magnetic field of three-phase induction motor will be explained. To obtain the rotating magnetic field, the three-phase winding should be displaced by 120 degree electrical with respect to space, and the three currents flowing through the three winding should be displaced by 120 degree electrical with respect to time. These two conditions must be satisfied. This is a three-phase induction motor, this is stator, this is a rotor. For your better convenient, I have shown only three slots. Let these slots corresponding to R phase, these slots corresponding to Y phase, these slots corresponding to B phase. Since three winding should be displaced by 120 degree electrical, that means if I draw the three phase winding, suppose this is the R phase winding, this is the Y phase winding, this is the B phase winding, and if theta is the electrical space angle, if R phase is at an angle of theta, then this phase difference between R and Y should be 120 degree. This angle should be 120 degree and this angle should be 120 degree. That means if R phase turns n of R is the n phase cos of theta, then Y phase turns is the n phase cos of theta 120 degree phase displacement minus of 120 degree, and n of B is the n phase cos of 120 degree displacement plus of 120 degree, where n phase is the number of turns per phase. Now I have to apply a three phase supply to this three phase winding. Let the phase sequence is the R, Y, B. This is your three phase supply of frequency F Hz. Then a three phase current will be drawn from the supply. Let this current is the I of R, the Y phase current is I of Y, the B phase current is I of B. Therefore, the three phase current displaced by 120 degree electrical with respect to time. That means if I draw the phasor diagram, then this is the I of R, this is the I of Y, this is the I of B, and this angle should be 120 degree, this angle should be 120 degree, and this angle should be 120 degree. If omega t is the electrical time angle, then I of R is the Im cos of omega t. I of Y is the Im cos of omega t 120 degree phase displacement minus of 120 degree. I of B is the Im cos of omega t plus of 120 degree, here Im is the maximum current per phase. The MMF is given by ampere turns. Ampere current into number of turns. I into number of turns. Therefore, the MMF of each phase can be calculated as MMF of each phase. That means the MMF of R phase is given by this current, R phase turns, that is equal to I of R into N of R is the Im cos of omega t into N phase cos of theta. Similarly, the Y phase MMF f of y is the Iy N of y, that is equal to this current multiplied by this turns Im cos of omega t minus of 120 degree N phase cos of theta minus of 120 degree. B phase MMF f of B is the B phase current, B phase turns, I of B into N of B, that is equal to Im cos of omega t plus 120 degree into N phase cos of theta plus 120 degree. Now the resultant MMF due to three phases R, Y, B is calculated by the resultant MMF f of R is the phasor sum of three phase MMF f of R phase, Y phase, B phase. If I do the summation of these three f of R, f of Y, f of B, then I can easily minimize this equation. The resultant MMF f of R is given by 3 by 2 f of m cos of theta minus of omega t. This is the equation of resultant MMF, where f of m is the maximum MMF, that is the Im into N phase. Now this is the resultant MMF produced in three phase induction motor. The resultant MMF changes its position with respect to angle theta. Theta is the space angle, and with respect to time angle omega t. Therefore, if I draw the resultant MMF f of R versus space angle theta, then when omega t equal to 0 degree, that means this is 0 degree, f of R, resultant MMF f of R is a 3 by 2 f of m into cos theta, since omega t equal to 0 degree. That means this is a cosine function, cos function. If I draw the fr versus theta, then it will be like this cosine function. where omega t equal to 0 degree. When omega t equal to 45 degree, then the resultant MMF is the 3 by 2 Fm cos of theta minus 45 degree. That means it will be progressive 45 degree. The function will be like this. Here omega t equal to 45 degree. When omega t equal to 90 degree, then f of r resultant MMF is the 3 by 2 Fm cos of theta minus of 90 degree, that is equal to 3 by 2 Fm cos theta minus 90 degree, that is equal to sine of theta, sine function. That means if I draw the waveforms, that will be like this. Omega t equal to 90 degree. That means from the graph, it has been shown with respect to a space angle, the resultant MMF Fr is continuously progressing into the forward direction. Therefore, it is called a rotating magnetic field. That means the field which resultant field which is generated in this induction motor rotate into the forward direction at a speed of ns. The speed of the rotating magnetic field is ns, where ns is called the synchronous speed and it is given by 120 f by p. Now, if I do the reverse of supply voltage, that means if I interchange any two terminal of the supply voltage, suppose this is R, this becomes B, this becomes Y. By reversing the supply voltage, that means interchange any two terminal, then this is the B phase, this is the Y phase. That will be the plus 120 degree, that will be the minus 120 degree. And the resultant MMF will given by, it will be the f of B is the f of Y, and it will be the plus theta plus omega t. That means the resultant MMF will progress into the opposite direction, in this direction, f of r dash. The conclusion is that by reversing the supply voltage, the direction of the rotating magnetic field will be opposite. Now, we have seen that if these two conditions is satisfied, the three-phase winding displaced by 120 degree and the current which is drawn from the supply displaced by 120 degree with respect to time, then a rotating magnetic field will be produced which rotates in the forward direction at a speed of ns, which is given by 120 f by p. Thank you once again.